This is a presentation about wireless LAN basics. Well, wireless LAN, as you can guess, it doesn't require any cabling between communicating devices. Radio waves are used for transmission between the media. Wireless networks are everywhere. We use smartphones, laptops, tablets, and many other Wi-Fi devices every day. Wireless for industrial applications is also not an exception. Wireless is getting more and more popular for many industrial applications in these sectors: transportation, machinery, oil and gas, etc. Radio wave is an electromagnetic wave in certain frequency range, so the main characteristic of the RF signal is its frequency. To generate this frequency, we use an RF transmitter. To receive, we use an RF receiver that is specifically tuned to its transmitted signal frequency. This slide contains a comparison table between wired and wireless networks, so you can see the main differences. Please note that in the case of wireless communication, there are no collision detection mechanisms. However, collision avoidance principles are used instead. Besides, wireless signals are highly affected by noise and interference. It can be affected by any device within transmission coverage area. There are a lot of wireless communication standards on the market. Most popular ones are shown on this diagram. Vertical axis represents communication range, while the horizontal axis represents data rate. Zigbee, Bluetooth, and Wi-Fi are all used in local area communications. However, Wi-Fi provides the best speed performance among them. Wi-Fi is commonly used for naming the 802.11 standards group. The main reason behind why Wi-Fi is so popular is because it uses unlicensed frequency ranges of 2.4 GHz and 5 GHz. There are 4 802.11 standards that are currently being used for industrial applications: A, B, G, and N. Newer AC standard is coming soon. The main differences between these standards are frequency range and throughput. The legacy B standard supports up to 11 megabit per second of data rate. A and G can go up to 54 megabit per second of data rate, and N can achieve up to 300 megabit per second data rate and even up to 600 megabit per second data rate depending on transmitter's configurations. The numbers that I just mentioned are theoretical maximum data rates, but you shouldn't be misled by these values. Actually, Wi-Fi uses almost half of the bandwidth for network overhead. It includes management frames, headers, error checking, transmission acknowledgement mechanism, and so on. For example, the actual maximum throughput for 802.11g standard when connected at 54 megabit per second data rate is roughly around 20 megabits. 2.4 GHz range is used by B, G, and N standards. The range is divided into 14 channels. Each one has around 20 MHz width. However, depending on local regulations, some channels may be restricted for use. For example, in Europe, channels 1 through 13 are available, but in the US, only channels 1 through 11 are available. In Japan, 1 through 14 channels are available. These regulation differences are the reason wireless device vendors have different models for different regions. For MOXA products, we use EU, US, and JP suffixes in our model name. It is important to keep in mind that channels from 2.4 GHz range overlaps. To reduce interference, it is recommended to choose non-overlapping channels in the same area. For example, 1, 6, and 11. 2.4 GHz range offers longer communication distance comparing to 5 GHz range. Another advantage is popularity of this range. Almost all Wi-Fi devices on the market can operate at 2.4 GHz. However, the negative side effect is that this range is overwhelmed, especially in crowded areas. The overlapping channels can be troublesome, causing more interference. 5 GHz range are used by A and N standards. Please double-check your country regulations for this frequency range. 5 GHz are not so popular. All of the channels in this range has no overlapping channels. You will generally get less interference and better performance with 5 GHz. However, you must choose the appropriate devices that can support it and also check your local regulation standards for your country. Now let's talk about antennas. Antennas are used to transform an electrical signal into radio waves and vice versa. It means that if you want to enable wireless communication, you would definitely need some kind of antenna. The main antenna characteristics: frequency range, direction diagram, gain, and polarity. To better understand antenna principle, you need to understand the concept of isotropic radiator. It is a theoretical antenna that radiate equally in all directions. Real antennas cannot radiate in all directions with equal power, which is why we have a direction diagram to illustrate the real situation. Antennas are passive, so please don't be confused by the gain parameter. This is to show how much antenna focuses signal in certain area comparing to isotropic radiator. That is why gain is measured in dBi. This is a typical direction diagram of omni antennas. It looks like a circle in horizontal plane, but in vertical plane it looks more like the number 8. If you compare the top and bottom antennas, you can see that high-gain antenna has narrower diagram in the vertical plane. It means that high-gain antenna focuses the same amount of energy in a more condensed area, which gives us more signal level boost. Omni antennas are also called dipole, based on the design principle. Directional antennas focus signal in one direction in both planes, which gives us even more boost in signal. There are several directional antenna types, including Yagi, patch, and grid antennas. Let's summarize antenna types. Omnidirectional antennas has 360-degree coverage, at least in one plane, and as a result, it has a weaker signal. This is suitable for short-distance applications when the Wi-Fi client's location are not specific or when the clients are mobile. Omni antenna can be used to set up point-to-multipoint connection. Directional antenna has less than 90 degrees coverage but with higher gain. This makes a pair of directional antennas a perfect solution to establish a long-distance point-to-point communication. Antennas should be aimed at each other in a fixed position. When choosing antenna, make sure that frequency range, gain, and direction diagram are suitable for your application. Also, antennas that work in pair should have matching polarity. VSVR stands for Voltage Standing Wave Ratio. Anything below 2 to 1 should be fine. Impedance should be 50 ohm for Wi-Fi antennas. Finally, make sure that both connections match on the antenna and on the device. Hence, use special connectors to connect them if necessary. This slide shows typical gain range depending on antenna type. Gain values affects not only transmitted signal but also sensitivity for receiving signal. We recommend the following steps for wireless system deployment. First, make sure that antennas has matching polarity. Second, perform power budget calculation to evaluate transmission distance. Third, perform site survey and choose the least occupied channels. Fourth, find optimal antenna height, placement with maximum coverage and least amount of obstacles. Fifth, in case of directional antennas, use special utilities such as JPerf or Chariot to test your throughput and hence align and fine-tune the antenna positions. Basic RF system consists of transmitter, radio receiver, and antennas. To have a successful communication between them, both transmitter and receiver should be tuned to the same frequency and has sufficient signal level. Received signal power should be higher than the receiver's sensitivity. Decibel is the units used to measure signal power, including transmitter power and receiver sensitivity. Decibel is a logarithmic value that expresses ratio between two values. In our case, it is signal power. It can represent signal loss, for example. As you see from the equation here, it is actually a logarithm to base 10 of the ratio between measured power and base power value. If we agree to use a fixed base power value, decibel can represent an absolute value. Depending on base power value, we can have several commonly used decibel units. If you take 1 milliwatt as a base power, it would be dBm, or decibel milliwatt. If base power is watt, then the unit is called dBW, or decibel watt. Antenna gain is measured in dBi, which stands for isotropic decibels. This relates to isotropic radiator concept that I mentioned earlier. The greatest benefit that logarithmic system gives us is very simple calculation process. With decibels, we can replace division and multiplication operations with more simple addition and subtraction. You can use this reference table to convert decibel milliwatt into absolute value. To make sure that our wireless communication will succeed, we have to calculate signal power on receiver's side, taking into account the influence of our environment and system components. If the calculated signal power is higher than receiver sensitivity, we can then say that our wireless system will probably work. This slide is showing you typical components that you have to consider. The transmitter itself and antennas make positive contribution into signal power. Cables, connectors, and air, on the other hand, reduce signal level. Here is an example of such calculation. Our AP has a transmitter with power of 100 milliwatt. Let's convert this into dBm using reference table. The value is 20 dBm. This will go with a plus sign in our formula. Two cables and adapter has a negative effect on the signal, and thus we add -9 in the formula. Next component in the chain is antenna. It will focus our signal and increase it by 12 dB. Air loss for our case will take around 70 decibels. You can use reference books or internet to estimate air loss or signal loss for other materials. On receiving side, we have similar negative impact by 9 dB from connectors, cables, and positive impact by 12 dB from antenna. Summing up all these values, we get the result of -44 dBm. According to technical specs, our receiver's sensitivity is -85 dBm. Since -44 is much higher than -85, we assume that our wireless communication should work correctly. Here you can see some typical RF signal loss values against for different materials. Best case scenario is in free space or in a vacuum. Thick walls and ceilings can affect the signal a lot. To help you with the equipment selection and transmission distance estimation, we have prepared a special tool, Wireless Calculator, on our website for your reference. You can follow the link on the slide to check it out. Once you choose all components and parameters, you can estimate what sort of communication performance you can expect. Please use this only as a reference and perform on-site tests, as the real environment can have many unpredicted interferences. There are two Wi-Fi operation modes. First is called ad hoc. In this mode, Wi-Fi devices communicate without any intermediate equipment. They form point-to-point connections with the same frequency and same logical Wi-Fi network. Ad hoc mode is not so popular because it can lead to poor performance and security vulnerabilities. Second mode is called infrastructure. It assumes that we have special wireless intermediate devices that can form a network infrastructure and cover certain areas. Infrastructure mode defines two roles for Wi-Fi devices: access point and access client. Usually, access point has a wide connection to the backbone network, and it can also provide connection and accessibility for wireless clients to the backbone. Access points acts like an Ethernet switch with wireless interfaces. Also, access point provides security features and traffic filtering. Access client could be a wireless device that has another wired LAN segment behind it, or it could be just an end device like smartphone or laptop. In order to identify the provided service, access point creates logical wireless networks with different SSID. SSID is the name that you can see when you scan surrounding area with your phone or laptop. Most access points are capable to create more than one SSID. Here are basic operation steps of AP and client. First step is scanning. In this step, client is figuring out what networks are currently available. Once the user has selected a particular Wi-Fi network, authentication process begins. Authentication is a process when AP checks the client's identity and decides whether it accepts the connection or not. If authentication is completed successfully, AP will start association process to finalize establishing the connection. Once it is completed, then you can start to send and receive data. When client leaves the wireless network, the dissociation process will begin. Scanning could be active or passive. In passive mode, client is jumping through all channels trying to get a special message from AP that is called a beacon frame. AP would normally send this kind of frames periodically to inform potential clients about its presence. Passive mode consumes less energy on client side, but connection process takes more time. In active mode, the client will initiate the scanning by sending a special probe request messages on every channel. AP would send back the probe response to inform the client immediately. During authentication process, AP checks if the client is authorized to access the network. In case of open system authentication, no credentials are required from client. It then simply sends authentication request to the destination MAC address. AP sends back authentication response containing a success or failure message. Authentication failure may happen when client's MAC address is blocked by configuration of AP. Open system is commonly used in public places such as airports, restaurants, and so on. There are several ways to restrict access to your wireless network: WEP, WPA, and WPA2. These methods use a predefined shared key. It is a password that you have to use before establishing a Wi-Fi connection. WEP was historically the first one, and now it is considered not a secure method because vulnerabilities have been found. WPA and WPA2 are more modern and considered to be secured shared key authentication. To be more secure, 802.1x enterprise authentication with Radius server can also be used. WPA2 is the recommended method since it is the most sophisticated one. To protect your data, Wi-Fi offers encryption with TKIP and AES algorithms. After successful authentication, association process begins. During association, client and AP negotiate about communication parameters, such as data rate. Finally, client gets association ID, and AP will allocate necessary resources for the client. Once association has successfully finished, data transmission can begin. 802.11 standards also define one more function of wireless devices. It is called WDS, and it is designed for building a wireless connection between access points to form wireless backbone. This function has performance and security issues, which are why it is not popular nowadays. We will talk about wireless backbone in more details in the next section.